through the questions now, focusing more towards the sort of gravity orbital ones. We'll run through some projectile ones very quickly. So here you've got an example, object undergoing projectile motion, and they're asking again about the horizontal and vertical acceleration. As we discussed when we were talking about this, this is commonly tested. So of course you understand horizontal has no acceleration, vertical is 9.8, and so the answer of course will be D. Question 2, testing hypothesis for maximum range. So this is more a question of experimental setup. Okay, you want to test the hypothesis that the angle of projection versus range. So of course, you really should be looking at a launch speed that is constant because that's a control variable. And then you have a varying that. Launch speed varies, it's not good. This one has a launch speed of 3, and this is varying angles. This is launch speed of 1 to 5, so that's not suitable. Now, both of these in some ways are suitable, but it says best test the hypothesis. I suppose it's not very clear. I mean, both of them would, but I guess if you want to really truly test, and assuming you've got equipment that is accurate enough, whether an angle of 45 specifically would give you the maximum range, as opposed to just because if it's 35, 45, 55, you don't know if it is 45, it could be 46, 47, could be 44, 43. This one would more clearly test the 45. Both B and C would test whether the range is affected by launch angle. But to be specifically getting an angle of 45 or a more close idea, B will probably be a better test. And the other reason why B will be a better test is because the launch speed is higher. If the launch speed was low, then the difference in range will be very small. And that's why I was also saying, depending on if you can actually measure that launch speed. Okay. Now, as a result of the sort of difference in the launch speed being higher, then hopefully, even though the change in angle is small, hopefully we can still detect it. And if we can, then this is a better way to test that. Okay. But A and D are definitely wrong. C is your next best choice. But for this specific question about angle of 45 being given the maximum range, B is the better choice. Okay, so here you've got a projectile motion, P is max height, ignoring air resistance. What's the speed of the ball at point P? So we know, of course, that this is the maximum height. That means there is no vertical velocity. However, do remember, it still has a horizontal velocity. And that horizontal velocity is constant, which of course is ux, which of course is u cos theta. See. All right, and this basically is just going to be covered in that we said earlier, right? Horizontal vertical components of velocity are vx, vy. We literally did this earlier, so you should hopefully see that your vy is going to go down and vx will be so v. So you can see why I say those things we covered are commonly tested. All right. Question about this. How long does it take the ball to return to initial height above the ground? So that's time of flight. We literally did that. It hits a stationary outfielder. Assuming the ball is hit, the outfielder begins to run towards the plate with constant acceleration. What's the magnitude of the acceleration if you catch the ball when it's 0.5 meters above the ground? So you'll basically be working out range. Okay. So that one, it might be worth doing because I guess it might be relatively more difficult. Okay, so I'll just quickly do A and B. So you know it's hit with a velocity of 28, angle 30 to the horizontal, 1 meter above the ground. You want to return to the initial height. So basically that means we're looking for time of flight. So if we let this be the origin, if we start this at 0, 0, then we basically let sy equals 0, solve for t, because when you get to 1 meter, there's no change in displacement. So that means 0 equals 28 sine 30 t minus a half g t squared, which is going to be 14t minus 4.9 t squared. You can take out t, which is 14 minus 4.9 t. So that, of course, means t equals 0, which we discard, or t equals 14 over 4.9, which, as a number, is going to be about 2.85 seconds. All right. B, the ball is hit directly towards a stationary fielder who is 85 meters from the plate, and then they become running. So basically, here's the ball. Here's the fielder 85 meters away. You hit the ball, and the fielder starts running. And they're going to catch it 0.5 meters above the ground. So it was 1 meter off the ground. It's going to fall to 0.5 meters above the ground. Now, you want to work out, she's run at constant acceleration, not constant velocity. You want to work out the magnitude of acceleration if she catches the ball when it's 0.5 meters above the ground. Okay. So when she catches the ball, she will have run some distance. Let's call that d. She would have run some distance d to get there. So what we could do is we could work out what d is. And we can work that out because we can work out the range of the ball when it's 0.5 below. Now notice it starts at 1 meter high and it goes to 0.5. So we can't really use this time. Okay. We know it's more than 2.86 seconds, but we could need to work that out. So we'll do the same thing again, except this time we let sy equals negative 0.5. It's gone down. And so negative 0.5 equals 14t minus 4.9t squared. We can move everything to one side. 4.9t squared minus 14t minus 0.5 equals 0, and times everything by 2. Now, to solve this, use the quadratic formula. Which of course is negative b, also minus the square root of b squared minus 4ac all over 2a. And that gives you 2.89 seconds for the positive answer, which we did expect because it's slightly longer than the returning to the same height. Right? It's got to return to the same height here before it falls even further. Now we can work out the negative answer, but it'll be negative, so we don't really want that. So that's the time we care about. Now, of course, the range, how far it's going to cross, is then going to be u cos theta, ux basically, times the time. So that is going to be 28 cosine theta, which is 30, times your 2.89 seconds. So we'll get your calculator to do that. And that gives us an answer of 70 point. Well, that makes no sense. Oh, it does make sense. Okay, I've drawn it the wrong way around, is what's happened. So it's 73.14 meters. Okay, so I've drawn it the wrong way around. Instead of running out, the fielder's running in. Okay, so actually, what's actually happening is the ball doesn't reach the fielder. So the fielder is somewhere out here. I mean, the question wasn't clear, I think. It just says runs towards, and I wasn't sure if that was out or in. So the fielder's starting here, and they're actually running in to catch the ball at some point D. I mean, that's what our calculations show. And so that means this ball is actually falling down here. And so the ball is caught here, 0.5 meters above the ground. And now what we have just worked out with this 70.14 is we've worked out that this point here we've worked out that this is 70.14. So if you know the fielder starts 85 meters away and that they're catching the ball at 70.14 meters, we can now know that D is 85 minus 70.14, which is 14.86. So we know now that the fielder has traveled 14.86 meters. So the fielder has traveled a distance of 14.86 meters in 2.89 seconds with a u equals 0 because they started to run. Right, it's a stationary fielder, and at constant velocity, constant acceleration. And now you just use your Subat. Okay. If you consider your Subat equations, you've got v equals u plus at, s equals ut plus half at squared, and b squared equals u squared plus 2s. Now, the most applicable formula would appear to be using s equals ut plus half at squared, because of course we know t, we know s, and we need to find a. So we will now sub in our values. So 14.86 must equal u, which is 0, plus half a times t squared, which is 2.89 all squared. So basically, with a little bit of algebra work, your a will be 2 times 14.86 divided by 2.89 all squared. Which then gives you an answer of 3.56 meters per second per second. And that there on your left is your answer. For 4 marks. Great. All right. Let's move on. So that's fine. We'll just skip that. Okay, so this is more experimental error, but question, but I think many students have trouble with that. So let's have a look. So the diagram shows a camera and a ruler set up to obtain data about a projectile's motion along the trajectory shown. The entire trajectory is visible through the camera. Okay. Identify one of the errors in the setup and describe the effect of this error on the results. Okay. So I think one of the key things, I mean, take a look at this, right? But here is the center of your projectile motion, but the camera is set up here. So the camera is sort of off center. And if the camera is off center, that means it's going to get a parallax error, okay? Especially if you're relying on this meter ruler. And it's also problematic because this meter ruler doesn't run for the whole length. There's a few mistakes that we can pick out, right? We're going to focus on one for our answer, but for one thing, the camera is off center. The camera should be in the center of the projectile motion. And secondly, the meter ruler is not lined up. So, I mean, obviously you can account for that by taking it away, but I mean, that may be another potential source of error, especially if they don't offset, right? You should measure starting from 0. If you measure starting from 10 centimeters, that's fine as long as you account for that. But if you're just taking a reading off the meter ruler to then say do that, then of course you're going to get an issue as well. Now, combined with the fact that the camera is off center and that the meter is offset from the wall, which is pointed out, good work. But because of those two combined, then you'll have what's called a parallax error. Because now this can now read like that there'll be a difference to where it actually is. I'll exaggerate it. Right? So basically, keeping this in mind, I mean, there's a few errors we could talk about here, but you can say that the meter, like one of the errors basically is parallax error, which is a result of the off-center camera plus the meter ruler not on the wall. And that, in this case, with this setup, will result in a range reading. What are we trying to read up? Well, it just says motion. So it will mean that the range will be reading will be lower than actual. Good. Using the graphs, describe velocity and acceleration. Okay, so just very quickly, we know what we expect, but in this case, you've got horizontal displacement. This is displacement time graph with a straight line. Of course, the gradient of a straight line is velocity. So this shows velocity is constant. This is a velocity time graph with a relatively constant gradient. Again, the gradient of a velocity time graph is acceleration. That shows you acceleration is constant. Okay. Some more questions. So a lot of the times, we won't do this question, I think, because we want to get onto some other ones, but a lot of times students ask for projectile motion. So if you take a look at this question, it's talking about a projectile. So you're launching the projectile and some projectile motion. And so one key point we stress about projectile motion is that the only force acting on the projectile is gravity. We assume no air resistance and the only force is gravity. And students often say, well, surely you had to have a force to launch the projectile. And that is true. You have a force to launch the projectile. But when we study projectile motion, we don't care about the launch phase. We don't care about the forces during the phase that we're launching it, which does happen. We only care about after it's launched, the moment it's left. Now, can you get questions about the launch phase? Yes. That's your year 11 question on dynamics, right? You've got some force over some period of time, you calculate work, blah, blah, blah. Or F equals ma, or impulse, or whatever. This is a question combining both, right? You've got a spring launching the projectile, and then they want you to use your year 11 work from elastic potential energy to basically calculate the launch velocity of the projectile. That's not a projectile motion question in and of itself. That's just an year 11 question on dynamics, which you should know how to do, okay? Just because it's year 11 means it's assumed knowledge. But of course, once you've calculated the launch velocity, and of course the forces are involved to get it to launch velocity, then the question is calculate the range. B is the projectile motion question in that sense. A is just the precursor to the projectile motion question in that sense. Okay, we won't do that, but that hopefully answers some questions there. This looks fairly straightforward. Let's try to get to circular motion now. You can see there's a decent number of projectile motion questions, but we've covered and some of them are experimental in nature, but we've definitely covered quite a few. And just to give you very briefly something like this is multiple choice. Shows 2 consecutive shots by the batsman. Both balls reach the same max height, but ball Q travels twice as far as P. Which of the following is different for balls P and Q? Now, if you weren't aware of what we said earlier, then this question could be a lot more troublesome and take you a lot more time. But we already said, if balls have the same max height, then they must have the same time of flight. Of course, that means they don't have different time of flight. And they clearly don't have different gravitational forces if they are the same ball, which, I mean, 2 consecutive shots. In cricket, you assume it's the same ball, that they didn't change balls. The gravitational acceleration we know is 9.8. And so logically, either by elimination thus far, we know they have different initial velocity. In fact, we know that they have same time of flight. So the only reason that the range is different is because the horizontal velocity is different. The horizontal velocity is only different because they've got different initial velocity. And you can see how knowing that they have the same time of flight really saves you a lot of time there. All right, so circular motion. That looks a bit basic. Let's try to get one that's a bit more difficult. All right, so let's start here. You've got a horizontal disk is rotating clockwise on a table. So you know it's going clockwise. So we're drawing our top view. 2 small blocks are attached to a disk at different radii from the center. Okay. So draw a diagram of the scenario using vector arrows to show the relative linear velocities and central forces for each block. Okay, so if this is the center O, we will just make it clear. You've got radius. So we've got block 1. And block 2. Now, we understand that at any point, as we discussed, the linear velocity will be tangential. So if you think of this as a circle, basically, they're undergoing their own circular motion. So it won't be very easy to draw a concentric circle here. But you can think of it roughly like that, which means, of course, that the velocity will be going in that sort of direction. And this one will be going in a smaller concentric circle like that. So it means it'll be going the same direction, but slower, kind of thing. Okay, so that gives you the sort of idea. Same direction, but slower. Now, that's the velocities. Now, we also need to show the centrifugal forces. Now, you might recall that centrifugal force equals mv squared over r. Now, the centrifugal force by definition, means towards the center. The centrifugal force, which is normally not tested, is the one going outward, but the centripetal force is going inward towards the center always. So Fc equals mv squared over r, and we understand that they didn't really say it's the same block, but I think it's a reasonable assumption, okay? And the velocity is clearly larger for the further out you are. And so, I mean, it might not be very easy to tell from mv squared over r because v goes up and so does r. So honestly, it will be easier to tell. I mean, you can probably guess that the central force is bigger for the outer one, but it's probably even more clear cut if you think about it in terms of mr omega squared, where omega is the angular velocity. So for the same mass and the same angular velocity, and they will have the same angular velocity because they're both kind of being turned around on the same disk. That means the further out you are, as r goes up, the centrifugal force goes up. So we can then show that the centrifugal force is bigger for this one, and the centrifugal force for this one will be smaller. And that basically would be your answer, with your vector arrows showing the velocities for both and the centrifugal forces for both. Of course, being vectors, you must show both direction and magnitude. Okay, so here you have a car traveling at constant speed, follows a path shown. So the car is going this way around this roundabout. So since it's going around a roundabout, we can sort of basically assume that it's going in circular motion and it's going at constant speed. Okay. So we've got constant speed. That means you want to look at the acceleration because you're looking at an accelerometer. Now, during the circular motion, that will be v squared over r. And if it's constant speed and constant radius, that means this will be a constant. So at t equals 0, it's not entered the circle yet. Once it enters the circle, it will be undergoing circular motion. And then I guess it has to exit the circle as well. Okay. So there will be something happening at the start and the end. And then during it, we will have a constant acceleration. So A is definitely wrong because it has no acceleration in the middle. And we know that it must have acceleration in the middle. Now, then the question is, what's the direction, right? So we understand that the acceleration is going to go, I guess, at this, in terms of the circle, it's going to go like this, right? So the acceleration at this point in the circle is kind of going to the right. At this point is down. At this point is left. At this point is up. Now, they've just said acceleration is positive or negative. And they did tell you that they're measuring acceleration in the x direction, right? That means they're measuring the lateral acceleration. So it's x bar. So basically, if you think about the car being here, for it to turn, it must have accelerated towards x prime. It has to accelerate towards x prime to turn left to start with. Now, if it's measuring in the x prime direction and you're sailing towards x prime, that gives you one direction. And I think if they're saying in that direction, they haven't defined which way is positive, but I mean, it's either positive or negative. But the point is, whichever sign that is, think about when it needs to exit, right? When the car needs to exit, it's facing this way. So at the start, it's accelerating left to enter. It's turning left to enter. When it comes out, it's turning left to exit, right? Left to enter, and then left to exit. So your acceleration direction at the start and the end must be in the same direction, which unfortunately doesn't help us because it is in the same direction for both B and C. So it's not D because you will need that little bit of a start. Now, look at this, right? Once you turn left to enter the circle, your acceleration is to the right the whole time, to the right of the car, right? As the car goes through the circle, it's in the circle now. As far as the car's concerned, the acceleration is to the right of the car all the time. Make sense? as the car is going around, the acceleration is towards the center, which is the green arrows. But if you're sitting in the car, that means you're accelerating to the right. In other words, towards x. But to enter the circle and to exit the circle, you had to turn left, which means you're accelerating away from x, towards x bar. So that means that acceleration in the middle during the circular motion is going to be opposite to the entrance and the exit. So that means it's not C. And so your appropriate answer would be B. Okay. So from the perspective of the car, you would start with an acceleration leftward to enter the circular motion. Once you're in the roundabout, you'd have a constant rightward acceleration until you exit again with a left. Let's try and find a... Okay, so now we're getting into the sort of satellites, okay? So remember, with your satellites, you basically have your straightforward calculations. So you've got a satellite moving a circular motion of radius around Earth. Key point to note is that this is the radius of the orbit, which is great. If you're given the altitude, as you are often given, you're going to need to add the radius of Earth on top, okay? So the speed of the satellite is 8.1 times 10 to the 3 meters per second. What's the central acceleration? This is just a straightforward calculation. Central acceleration is equals v squared over r. Sub the numbers in, get your answer. Nothing difficult about that one. Okay. Now, a satellite is in orbit around Earth with tangential velocity as shown. Which of the following describe the direction of the central force acting on the satellite? Well, the central force is always towards the center. Okay. So it's going to be towards that way. So it will be in the same direction as the gravitational force. Definitely not opposite. It's definitely not in the same direction of the tangential velocity or opposite, so it's clearly A. Let's try. Now, here, the mass is attached to a length of string moving in a circular path around a central point. Now, the string breaks at this point. What line best dissects the subsequent path? So if the string breaks, that means there is no more force from the string, no more tension, which means the object is no longer undergoing circular motion. And so by Newton's first law, it will continue in its current path in a straight line. So answer B. We've just done a very similar question to that. So now you just need to write a written response, okay? So we won't do the same question, but you can see this sort of concept comes up. So just make sure when you're doing this question, you're assessing the statement that they've given here. The statement says there's no net force acting on the car because speed is constant and the friction between the tires on the road balances out the central force acting on the car. Remember, when you're assessing a statement, you need to say what's true or false. It's either entirely true, entirely false, or partly true and partly false. And if it's partly true and partly false, then identify what's true and what's false. And for this question, you need to talk about the horizontal forces with your data. Brief rundown, no net force acting on the car is clearly false. And you would support that by saying, as we've said before, if it's going in a circular motion, means that the velocity is changing direction because it includes direction. And therefore you have acceleration, which is equal to AC, which is equal to v squared over r. And in this case, you would calculate it. And that then specifically means that we would address the fact that it's false because although speed is constant, we would put that in here. Although speed is constant, velocity is changing because velocity has direction and hence acceleration. So we would specifically address that part of the statement. We will then talk about how, because you have constant required acceleration, this needs a force. And again, we will calculate that using the data we've got, give a numerical answer of the force required. And then we would address that saying that this force is actually provided by the friction between the tires and the ground. Okay. It doesn't balance out the centripetal force, it provides the centripetal force. And therefore, while part of the statement is true, that is, the speed is constant, it is definitely false that the net force is zero. The net force is provided by the friction between the tires, which provides the centripetal force. And rather than balancing it out, it is the centripetal force itself. That gives you an idea of the sort of things you would want to say for an assessment question. Okay. Focusing a bit more on orbits, you've got a satellite moving in uniform motion around Earth. F is the force, v is the velocity. Hopefully it's clear at this point. Force is towards this, is the gravitational force. So you're looking at A or C, definitely not B, definitely not D. Okay. And velocity will be tangential to A. This is a question comparing projectile motion and circular motion, it appears. You shouldn't have too much trouble with that. Just make sure when you're looking at question C, when it asks you to describe and compare forces, that you actually do describe them both separately and compare, which means provide similarities and differences of the forces at max height. Comparison of forces basically needs you to know your year 11 work. Think of what forces apply to your object. Do you have gravity? Do you have normal? Do you have tension? Do you have friction? Those are the key things you would generally be looking at. But basically, it's your year 11 skills that you need. And then use that, apply it to your objects A and B to then both describe and compare them. Okay. So now we're starting to move into satellites a bit more. So a satellite is orbiting a planet at a fixed altitude. So the row identifies the magnitude of the work done by forces on the satellite and the reason for this being the case. Well, if it's at a fixed altitude, then the GPE is not changing. Because the GPE is not changing, then ideally no work is done on the satellite, because gravity acts as 90 degrees angle to the direction of motion of the satellite. Answer will be B. There is a force acting on the satellite, but remember, work equals force times displacement from your year 11, but it's the force that is parallel to the displacement. Because your velocity is tangential, and to your force, the gravity is always acting at 90 degrees. So therefore, the horizontal component is 0 times the displacement, so it's always 0. That's why in perfect circular motion, you're never doing any work on the projectile. Planet X has a mass twice of Earth. The acceleration due to gravity on the surface of this planet is half that of the planet of Earth. If the Earth has a radius of 1, what's the radius of planet G? This would need you to just use what we've talked about before, G equals Gm over R squared. And keeping in mind that for Earth, that you've got G of Earth equals G mass of Earth over radius of Earth all squared. Now, you're told planet X has a mass twice of Earth, and the acceleration is half. So then you just stuff it in, basically. So mass of X equals 2 times Earth, and the G on X is half the G on Earth, and radius of Earth equals 1. Find radius of X. All right, well, we know that G of X equals G mass of X over radius of X all squared. That's pretty clear. But G of X is half times GE. And the mass of X is 2 times mass of Earth. And half of GE we can replace on the left-hand side with what we've just worked out. And then you can have fun cancelling. G cancels with G. Mass of Earth cancels with mass of Earth. Radius of Earth equals 1, so that goes. So you're left with basically the half here, the 2 here, and the Rx squared. Basically, you'll get Rx squared equals 4, or Rx equals 2. I'm going through these a bit more quickly to hopefully be able to go through a bit more questions, and hopefully you can review it at a later stage at your own pace. All right, so here the table shows data about the solar system. You've got planet and Earth, average distance and period. This very quickly should allude to Kepler's third law that we covered earlier. Now, if you're doing it with 2 planets, both orbiting around the sun, then as I mentioned before, you don't need to do unit conversion. Just make sure they're both the same unit, in this case, astronomical unit and days. Excellent. And so basically, what would be the period of another planet if it orbited the sun at an average distance of 3.5? So we don't even need both, really. We just need, if they wanted just another planet, then it's really just r cubed over t squared equals another r cubed over t squared. And we could just pick any one of these, really. Earth is an average of 1 and period of 365 days. So you can have 1 cubed over 365 squared for Earth is equal to 3.5 all cubed all over t of the planet you want squared. And you solve for t. Use a calculator, find t, and that is the same. And Kepler's law specifically does say that the ratio is the same. That's specifically what Kepler's law says. So really, if we take r cubed for Earth over period squared for Earth versus for Mercury, we should find it the same. I'll skip that because there's no reason they should be different, but if the data is correct, they definitely should give you basically the same answer. Okay. So now I've got escape velocity and orbital velocity involved. 2 identical masses are placed at points P and Q. The escape velocity and circular orbital velocity for the masses at P and Q are as given. The escape velocity and circular orbital velocity of mass Q are also as given. Diagrams drawn to scale and X denotes the center of Earth. So when they say it's drawn to scale, you want to take a ruler and kind of sort of measure. But eyeballing it, it looks like the radius of P is related to the radius of Q. So the radius of Q looks like it's double the radius of P. But in an exam, use a ruler and check it. Okay, but it looks kind of like that way. The velocity of for a body in circular orbit is given by that. Okay, they've been very nice in giving you the formula. What's the value of escape velocity of Q versus orbital velocity of P? Well, we know escape velocity is root 2 gm over r, right? In other words, it's root 2 times orbital velocity. We covered that earlier. Now, basically, the escape velocity of Q would equal root 2 times the orbital velocity of Q. Okay. And then we can just compare the orbital velocity of Q versus the orbital velocity of P. Now, if you can see that the orbital velocity, so basically the orbital velocity of Q is going to be the square root of 2, is just going to be the square root of gm over, let's call this r. That this means this will be 2r. So this will be 2r, which will be the square root of a half times gm over r, which is the square root of a half times the square root of gm over r, which is hopefully clear that it's 1 times root 2 times the orbital velocity of P. So that means you've got root 2 times the orbital velocity of Q, which is 1 over root 2 times the orbital velocity of p. And you can see that the root 2 cancels. And that just gives you the orbital velocity of p, which means 1 is your answer. As we've discussed before, the further out you go, the orbital velocity decreases. So Q has a lower orbital velocity and escape velocity because it's further out, whereas Q has a higher orbital velocity. I'm not sure if I said the right thing. Let me just repeat. The further out you go, the escape velocity goes up. Let me repeat. The further out you go, the escape velocity goes down. And the orbital velocity also goes down. As you go towards the center, the escape velocity goes up. And the orbital velocity goes up. Okay, so that's just an explanation of Kepler's second law. Okay, that's very standard. Once you know what Kepler's second law is of law of areas, you can go and revise that. There's nothing special there. Probably want to talk a bit more about this question. So we've got a rocket carrying a satellite is launched from Earth. Once the rocket is switched off, the satellite continues in an elliptical orbit. Explain the changes in orbit during this journey. So for 3 marks, you want to talk about how, if you're launching from Earth, the energy, and I'll do it in a bit of point form to save a bit of time. We're converting chemical potential energy in the fuel to, I guess, heat, which then is being converted into thrust and forces. So as far as energy goes, it's being converted both, because you're heading up, into kinetic energy and gravitational potential energy. At the start, you're really trying to get the rocket going upward. So most of it is a lot of it is going to go towards, a higher ratio is going to go towards GPE at the start. That's why rockets launch straight up. And the reason they do that, by the way, is because, well, the further up you go, the more you're going to get the further up you go, the less air resistance you're going to get. And also the further up you go, the lower gravity is. So you really want to get up before you really spend the time trying to get faster. Okay. Once you get a particular altitude, then you're going to then convert later. You will then turn sideways and increasingly convert to KE and less GPE until ultimately you're only going for KE. Okay. So you're converting chemical potential energy into KE and GPE. Your GPE is continually increasing, but staying negative, and your KE is continually increasing. Now, once the rocket engine is switched off, there's no more energy given. So once engine switched off, then the total energy is constant. But because you are undergoing an elliptical orbit, we might want to talk about how the amount of GPE is not constant and your K is not constant. So that means when you are closer to Earth, so the technical terms are apogee and perigee, but when you're closer, that means you have GPE has reduced and KE goes up. And as you continue the orbit, so at the closest point to Earth, you do have GPE, but it's the lowest point. It will have the lowest GPE, and as you continue your orbit to the furthest point, your GPE will go up and your KE will go down, which coincides with what we said with Kepler's second law, that as you go further out, you'll slow down. As you come further in, you'll speed up. So since you're undergoing this elliptical orbit, it's kind of like having a rock that just keeps going up and down in midair. You'll have continually conversion from GPE to KE, and then KE to GPE, and vice versa. Okay. Now, the direction of the satellite's acceleration, remember, is always towards the gravity. So basically, it's got to be towards the center of Earth. So not that. That's probably closest to the center of Earth out of all the diagrams there. So A. Okay, it's not towards the center of the ellipse. It's towards the center of Earth. That's your gravitational pull. And in this case, it's an elliptical orbit, which does mean that, yes, it will speed up and slow down. Okay, unlike a perfect circular where it may not, the fact that you're orbiting in an ellipse makes it slow down over here and speed up when it gets there, as a result of the fact it's pointing towards a focus of an ellipse rather than the center of a circle. Let's see if we can get through one more question. Maybe I'll do this one. So consider the following two models used to calculate work done when a 300 kilogram satellite is taken from the Earth's surface to an altitude of 200 kilometers. You may assume the calculations are correct. Great. What assumptions are made about the Earth's gravitational field in models X and Y that lead to the different results shown? So here, you'll note that the work they use is Fs, which is mgh. So very simplistically, they've assumed that the Earth's gravitational field in X is constant. In other words, G is constant. In model Y, they've used, well, basically where you've got a variable gravitational field. In other words, G goes down as D goes up. And that's basically the difference that leads to the different results shown. And you can see that this gives you a 5.7 and this gives you a 5.9, which is probably not a huge difference in the grand scheme of things, perhaps. I mean, it's different enough to cause things not to work, but that's over a range of 200 kilometers. And so, which is still quite sort of close to Earth, right? It's still a low Earth orbit. It's as low as you can go pretty much for a low Earth orbit. So you can see why there is a small difference, okay? But obviously, as you go further and further out, that difference gets bigger and bigger and bigger. Why do models X and Y produce difference that, although different, are close in value? Oh, we kind of just accidentally answered that because of the fact that the radius of 200 kilometers is still quite close in this grand scheme of things. You know, the Earth is 6,400 kilometers in radius. 200 kilometers is notable and you are out at the border of space, but you're still quite close to Earth. Most satellites are above that. Even low Earth satellites are probably around 250 to 500 or 1,000 kilometers is low Earth. And when it comes to geostationary satellites, they're not to scale, is like 36,000 kilometers. So clearly 200 kilometers is not much. The point is you're still very close to Earth's surface in the context of space. You're still on Earth. Well, you're basically almost still on Earth. Calculate the orbital velocity for a satellite in circular orbit at an altitude of 200 kilometers. Okay, that should be very straightforward. You just sub in the values of G, M, and R, okay, and then you'll get your answer. All right, so we'll leave that there for today. Hope you found that helpful. Now, do some practice questions from this. You both have it. Do questions from it. And then tomorrow we'll be continuing looking at module 6.